Chapter 7, Continuous Probability Distribution. In Chapter 6, we talked about the discrete probability distribution. In this chapter, let's talk about the continuous probability distribution. We talk about the uniform continuous distribution, normal distribution, standard normal distribution, normal approximation to the binomial, normal approximation to the Poisson, and exponential distribution. Okay. Basically, in the continuous variable, events are as the intervals. In the discrete variable, as we said the last time, we talked about that last time, each value of an x has its own probability. But for a continuous variable, now the number can take any number, any value, right? Then there's an infinite number of values over the x-axis. So the events are not in individual point on the axis, but are intervals. And probabilities are the areas underneath a smooth curve. So a single point has no probability in a continuous variable, the case of continuous variable. In this case here, look at the chart here, for discrete variable, the probability is defined at each different point. For continuous variable, from 53 to 54, you can have infinite number of values in the middle, and we want to just keep it just a second, okay? So we can have infinite number of values in the middle. So you can only define the probability over a certain interval, not at any given point. Okay? For the probability distribution of a continuous variable distribution, we use the PDF, the Pfx, for its probability distribution function or density function. It must be non-negative because the probability cannot be negative. It's always above 0, right? And the total area under the curve must be 1 because that's all the possibilities. Right? And the mean, the variance, the shape depend on the PDF parameters. If you see, what is shown here is the miles per hour as a normal PDF, normally distributed PDF. For cumulative distribution function, or CDF, and we use fx to denote it. This shows the probability of x less than or equal to any value. Okay? And here is from 60 to 90 miles per hour. This is a cumulative distribution function. You can see the added probabilities is increasing, approaching 1. Okay. Probability in the continuous distribution, as we said, are as areas, not as any given point. Continuous probability functions are smooth curves. Unlike discrete distributions, the area under any single point, like this point here, is 0, but this is not meaningful. But the area between A and B, and the area under the curve, is meaningful. So the entire area under the PDF must be 1, as we said. Okay? Mean is a balance point of the distribution. Okay? For uniform continuous distribution, that is, for the value of x of this random variable taking the value between A and B, the probability is 1 over B minus A. And that curve, since it's a uniform distribution, so the probability is the same across the whole range of A and B, the values of it, from A to B. Right? And we know this is a rectangle because this is a flat line. Right? So for the rectangle, the area is what? This is the base times height, and the base we know is B minus A, so the height must be 1 over B minus A. So times 1 over B minus A times B minus A, or the height times the base, must equal 1, and that's the area under the curve, or in this case the rectangle. So this is a characteristic of a uniform distribution. Okay, anyway. As we just said. Okay. So this summarizes the characteristic of uniform distribution. In this case, A is the lower limit, B is the upper limit. The PDF is 1 over BA. CDF is X minus A over B minus A. The domain is between A and B. This is the mean. This is standard deviation. Very similar to discrete distribution. Okay. And for the CDF, before the point A, the probability is 0. At point A, it starts to grow up, right? Go all the way up to B, that reaches 1. Now this is the CDF, kind of like a special case of a normal CDF curve that we are used to, we're familiar with. Okay? Let's take an example here. Anesthesia effectiveness. We take anesthesia when a doctor, extract our tooth, or a dentist extract our tooth. An oral surgeon injects a painkiller prior to extracting a tooth. Given the varying characteristic of patients, the dentist views the time for anesthesia effectiveness as a function as a uniform random variable that takes between 15 to 30 minutes. In other words, some people may be numbed down in 15 minutes. Others may take up to 30 minutes. But all of us will be numbed down between 15 and 30 minutes. So X is between 15 and 30. We know this is uniform distribution, uniform random variable. So A is 15, B is 30. Now what does it mean as standard deviation? It means simply A plus B divided by 2, that's 22.5 minutes. Standard deviation, you plug in the number of A and B, you get 4.33. In other words, on average, a patient would take 22.5 minutes to get numb. Okay? The standard deviation is 4.33. Then, what is the probability that the anesthetic takes between 20 and 25 minutes? And that is to find the probability of X between C and D. C and D meaning being 20 and 25. And that is actually D minus C over B minus A. Okay? The D minus C is 25 minus 20. B minus A is 30 minus 15, was 5 over 15, is 0.33 or 33%. In other words, 1/3 of customers, people will be numbed down between 20 and 25 minutes. If you look at a chart, it's pretty obvious, right? You see here from 15 to 30, that's everybody. There's a 15 minutes in interval. And from 15 to 20, that's 5 minutes. 20 to 25, another 5. 25 to 30, another 5. So basically, if you want to calculate the area under between 20 and 25, right, that's basically 1/3 of total. So we can look at that from the chart. Next, let's talk about the normal distribution. This is probably one of the single most important statistical distribution that we will cover, we will use. It's widely used, very important, and very, very widely known. Okay? And someone, a German mathematician, Carl Gauss, between 1777 and 1855, this genius mathematician, he discovered normal distribution. We call it Gaussian distribution, or bell-shaped distribution. Right? And this distribution is defined by two parameters, mu and sigma. By now, we all know what they are, right? Mu is the mean or average. Sigma is the standard deviation. So the normal distribution is denoted as n for normal distribution, mu, and sigma, mean and standard deviation. The domain is from negative infinity to plus infinity, so it never reaches an end. And almost all areas under the normal curve is included in the range of mu minus 3 sigma and mu plus 3 sigma. In other words, from the average, right, from the mean of mu, if you add 3 sigma minus 3 sigma, three standard deviation on both sides, either side. That includes virtually everything. Okay. We'll look at the chart that shows better. It's symmetrical, and unimodal. There's one peak. So this is the PDF for normal distribution. We now discuss further as to how to come up with this. We just need to know, this is a distribution function, and domain is from negative infinity to plus infinity. The mean is mu, standard deviation is sigma. It's symmetric, bell-shaped, and unimodal. Okay. This is the curve of normal distribution. A normal PDF reaches a maximum at mu and has a point of inflection at plus 1 minus 1 sigma. This is the point here at the peak, maximum at mu. This corresponds to the mean. At this point here, minus 1 sigma over here, plus 1 sigma over here, that's the inflection point, right? You can see between here and this one point here, the curve kind of like curves down, and over from here to the middle, it curves up. Again, from this point to this point, it curves up. From this point, the inflection point, it curves down. Okay, there's a change of concave to convex in the shape. It's a bell-shaped curve, and we know many things. For example, the well-known IQ follows that curve. Many things, many averages, many means also follows this curve. Okay. The CDF for normal distribution is this. Basically, you start at mu, that's the inflection point. And from before that, it curves down. After that, it curves up, right? And approaches 1, as we know. That's the CDF. Characteristic of a standard normal. Because this normal distribution can take many shapes. It could be a fat and low, or skinny and tall, right? But that makes it easy, not that very easy for people to use standardized table to estimate. In order to use standardized table, we use a standard normal or standardized normal, right? Since every value of unit there is a different normal distribution, we transform a normal random variable to a standard normal variable. And then for the standardized normal distribution, the mu will be 0 and sigma will be 1. And how to do that? We use Z transformation. Z score is defined as x minus mu divided by sigma. So we take each and every one of the observation of the value in the data, right? Deduct the mu, the mean from it, and divide it by the standard deviation. We get Z score. And that Z score also follows normal distribution. But this new normal distribution, or the standardized normal distribution, has a mean of 0 and standard deviation of 1. And then everything, all the normal distributions, will be having the same shape. So we can use a standardized normal table in the back of your chapter of the book, in the back of the book. Okay? These are the characteristics of the standard normal. Again, the same formula, simplified formula, and mean is 0, standard deviation is 1. Okay. And this is the standard normal CDF. Again, the inflection point is 0. There's the 1 standard deviation, or minus 1, plus 1 standard deviation, or plus 1. And this is the normal curve. This is PDF. This is the CDF. Okay. And common scale from -3 to +3 is used because that includes most of the observations. And the entire area on the curve is unity. The probability at an even point, at the event point P, is the definite integral of f, and the standard normal functions can be used. And if you look at, I want you to look at the table C1 on your book, appendix C1. That allows you to find the area and the curve from 0 to Z and the Z score. For example, if you look at, want to find the probability of Z score of 1.96, if you turn to your page, you see that, right? From 0.0 to 1.96 in appendix C1, you can pause here, go to your book, and find out in the back of your chapter, back of the book, you find appendix C1, you find this area to be 0.4750. Now that's the probability of of between 0 and 1.96. Okay. Now, what is the probability of between minus 1.96 and plus 1.96? Because we know this normal distribution is symmetrical. So from minus 1.96 to 0, it should be the same as from 0 to 1.96. If this is for 0.4750, this should be 0.4750 as well, right? So between minus 1.96 and plus 1.96, we should add these two up. That give you 0.9500, and that's 95% of the curve. Speaking of this, I hope you recall something. Remember the empirical value we talked about, right? That is 2 standard deviation, you have 90% of values. Where is that coming from? This approximately 95%, this is where it's coming from. 1.96 is almost 0.2. Right? 1.96 plus is also almost plus 2. So between minus 2 and plus 2, you have about 25%. And that is the basis for the empirical rule. Now let's revisit our empirical rule. The empirical rule says that it's about 68% of area under the curve is between 1 sigma. From here to here, 68.34%. Approximately 95% of area is between 2 sigma. From minus 2 to 0.2 is 95.44. We know between 1.96 minus and plus is 95% exactly. But between 0.2 and 2 is 95.44. And between 3 standard deviations, minus and plus, the area under the curve is 99.73. Now that's almost everything. Okay? So this standard normal distribution, the standardized table, is the basis for the empirical rule we talked about in previous chapters. There's also Appendix C2 in the back of your book. Appendix C2 allows you to find the area under the curve from the left of Z. Instead of from 0 to the Z point, it's everything to the left of Z. Here, 1.96. That is a 0.9750. If Z is a minus 1.96, table C2 will give you this little area, shape here, area here, 0.025, right? So you can use C1 and C2 to find your probability. They will give you the exact same answer, and it's just a matter of which one you want to use. Okay. Give you identical results. Use whatever is easiest for you. And you can use C1 and C2 to find the area of probability of any given Z score, Z values. And for example, you can also find Z's for a given area. For example, what Z value defines top 1% of normal distribution? Top 1%. This implies that 49% of area lies between 0 and Z, right? For top 1%. Therefore, the Z will be 2.33. By looking for an area of 0.49 in Appendix C1, Table C1, you find Z score of 2.33. So you can find the Z score to get the probability or area, or you can get the area to find the Z score, if using the same table. Let's look at example here, finding areas by using standardized variables. Suppose the student John took an economics class exam and scored 86 points. The class average was 75, standard deviation of 7. What percentile is John in? That is, for what is probability that someone scores less than 86? What is the area there? What's probability there? So for this question, what do we do? First, we need to calculate the Z-score. Z-score for John is X minus mu over sigma, or 86 minus 75 over 7. That's 11 over 7, or 1.57. Now that's Z-score. And that's the 1.57 standard deviations above the mean, above the mean, right? So where is John? We look at the chart here. This is 1.57. That's where John's score is. So we need to find the area to the left of John's score. And if we're using table C2, We find for z-score 1.57, the area is 0.9418. In other words, this area is shaded gray area is 1.9. Shaded gray area is 0.9418, or 94%. In other words, John is approximately at the 94th percentile. He scored higher than 94% of the students in his class. And of course, there are about 6% of students that that scored higher than him in John. Okay. Normal approximations. When can we use normal approximations? We can use normal approximation to the binomial. You look at this binomial distribution. Remember binomial distribution? That if n is large enough, right, then we can use a standard normal distribution to approximate it. Okay, and n becomes large, binomial bars become more continuous from here to here to here, more continuous, smooth, is more and more like a normal distribution. Okay, so when this approximation needed, the rule of thumb is if n times pi is larger than equal to 10, or n times 1 minus pi is larger than equal to 10, we can use the approximation. In this case, mu is n times pi, sigma is n times pi times 1 minus pi is radical. So we use mu and sigma. We have mu and sigma we can calculate. Okay. In the case of coin flipping, for example, if you flip a coin 32 times and pi is 0.5, this is binomial, right? Can we use normal approximation to the binomial? Since n times pi is 16, n times 1 minus pi is 16, they both are over 10, so we can use normal approximation. And then we can translate this discrete scale into a continuous scale, and then we can calculate. But before we do that, so what is probability of more than 17 heads in 32 flips of coin? That means that we can write that what is probability of the x is larger than 18, right? So more than 17 heads. More than 17 is actually between 17 and 18. Of course, we want to calculate that. So what is more than 17? It's actually between 17 and 18. We can use 17 and a half to denote that, right? So basically, since that's the cutoff for number more than 17, we use 17.5. And then we do that when that addition, we added actually 0.5 to the lower limit. That's called continuity correction. And this time we can do normal distribution to calculate. Okay. For example, in general, if say it's at least 17, we will use like 16 and a half for at least 17. More than 15, we can use 15 and a half to say more than 15. Fewer than 19, we can use 18.5 to denote fewer than 19, for example. Okay. What about Poisson distribution? Can we use normal distribution to approximate Poisson? Yes. When lambda is large, right? When lambda is larger than the one in the values in the appendix B, table B, we can use normal distribution. Okay? We also know in Poisson distribution, the mu is lambda, sigma is the square root of lambda. We have mu and sigma, we can do a normal distribution, normal approximation. This is an example of utility bills. On Wednesday between 10 a.m. and noon, customer billing inquiries arrive at a mean rate of 42 inquiries per hour at this energy company. What is probability of receiving more than 50 calls? Since lambda is 42, that's too big to use a Poisson table, we can use normal approximation. Mu in this case is lambda is 42, and sigma is square root of lambda, square root of 42 is 6.48. Okay? And then to find the larger than 50 calls, we use the halfway cutoff point between 50 and 51, and that's a 50.5. At this point, we can continue at normal distribution. Then we'll be done. Okay, that concludes. That is the end of chapter 7, and we'll continue next time.